Hello everyone, this is Rui PCB, your trusted PCB partner. Today we'll introduce the core concepts and practical strategies for double-sided PCB layout. After understanding the advantages of double-sided boards, let's learn how to approach professional layout. An excellent layout can make subsequent routing much more efficient and is the soul of high-quality PCB design. Remember the 4 golden rules: prioritize main components, use block layout, lay the foundation first, and ensure signal isolation. Rule number 1, prioritize main components before secondary ones. This means establishing anchor points for your layout. You can't just place components however you like. Layout should be strategic, like playing chess, where you first occupy key positions. The first step is to fix the structural components, those parts whose positions are already determined, such as USB ports, power sockets, mounting holes, buttons, and displays. These must be placed and locked in position first, as they form the foundation of your layout. Take our circuit as an example: the power socket on the side, the USB port, the switches, including this switch here. All of these have fixed positions, as do the components on this side. It might not be obvious when we look at the PCB layout, so let's take a look at it in the 3D view. The first point is that you need to place these switches, sockets, USB ports, and other external connectors first. This includes all the switches and connectors that serve as external interfaces. In most designs, their positions are already fixed because they need to fit into the enclosure. The mechanical engineer will provide you with a layout diagram specifying these requirements, so these structural components, these external interface positions, must be placed and fixed first. You can't just place them wherever you want. The second step is to place the core components. You should position the brain of the circuit, such as the frequency divider or processor, near the center of the board so that its distance to each edge is roughly balanced. In this circuit, for example, this is the 2P2040, a chip from Shuanpai, and it is basically placed in the center of the PCB because it connects to all other locations. You can see from these wires that it is connected to these sockets, to the switch connector on this side, and also to the 2 sockets on this side. This side mainly contains the power module, and it is also connected, so placing it in the center is more suitable for routing. Next, the third step is to place the key peripherals, keeping the MCU's essential components close by, especially the crystal oscillator circuit, which, along with its 2 load capacitors, must be placed right next to it. The closer the crystal oscillator pins are to the MCU, the more stable the clock signal will be, and the same goes for the reset circuit. So in this circuit, we can see right here, this cluster is the crystal oscillator and its 2 capacitors placed relatively close to the MCU. They can't be right up against it because the pin fan out needs some space, so you need to leave a little bit of distance. But they should be aligned with the pin positions, and this placement takes priority. Then, the reset button is placed quite far away, but it's only the button itself that's far. The corresponding reset capacitor and resistor are still placed nearby. The button is positioned at the edge because its location is determined by the device's structure. So, even though the button looks far away, the associated capacitor and resistor are still close to the main component. Next, Rule 2, block layout, group components by function. After identifying the key components, the remaining components should be grouped according to their functions rather than being scattered randomly. The modular approach divides the circuit into different modules based on their functions, such as the power module, MCU core module, analog signal processing module, driver module, and so on. Compact layout: place the components within each module closely together. The advantage of this approach is that it keeps the wiring within each module as short as possible, and the relationships between modules are clear at a glance. More importantly, it physically enhances the isolation between noise-generating modules and sensitive modules. Noise-generating modules are mainly those where the power connections produce noise. Sensitive modules refer to analog circuits, which are more sensitive to power supply noise, laying the groundwork for subsequent noise isolation. Let's take this circuit as an example again. The crystal oscillator, capacitors, and resistors related to the MCU are all arranged around it, and this here is its memory chip. Then over here is a set of power supply modules, and on this side is another set of power supply modules, so there are 2 sets of power supply modules. This is also reflected in this circuit, where a modular layout is used and related components are placed as close together as possible. This helps suppress noise, since power supply noise is usually generated in these areas. Components like capacitors and ferrite beads can be used to suppress its impact on other circuits. Rule 3, prioritize the foundation. Build a solid power and ground system. Power and ground are the foundation of a circuit and must be given top priority. Plan the ground plane. Before starting the routing, you need to clearly designate the bottom layer as a complete ground plane and try to maintain its integrity, avoiding running long signal traces on it. Look at this as well, Psi. In this circuit, it's obvious that there are fewer traces on the back than on the front because you want to leave as much ground plane as possible on one side. Don't fragment the ground plane too much or it loses its purpose. Next, place the decoupling capacitors. Each IC typically uses a 0.1 microfarad decoupling capacitor, and it must be placed as close as possible to the IC's power and ground pins. The path for power entering the IC should be VCC trace, decoupling capacitor, then the IC pin. This path should be as short and wide as possible, just like these capacitors. Most of them are decoupling capacitors. For decoupling capacitors, the power should come from the outside. Just like here, the power comes from outside to the decoupling capacitor first, then goes to the chip, not the other way around where it goes to the chip first and then to the capacitor. This direction must be strictly controlled. Next, plan the power tree. Power traces should be thicker than signal traces. After coming out of the power module, it's best to use a vertical or star-shaped structure to distribute power to each module, rather than connecting all modules in series with a single line. This helps reduce power coupling between modules. Let's take a look at the PCB layout. So this is a power supply. It branches out. Let's highlight the power trace so we can see it clearly. It branches out from this central point, which then forms a distinct tree structure. This particular branch goes to these specific components, and this other branch supplies essential power to the CPU and the memory chip. You should not make it into a large, continuous loop, so avoid routing in a circular ring. Both star and tree structures are perfectly acceptable. Rule number 4 is signal isolation. Let each signal follow its own path. You need to manage the signal routes on the board well to prevent them from interfering with each other. When arranging the layout according to the signal flow, try to organize the functions in the natural order from input to output. For example, input interface, amplification circuit, MCU, driver circuit, and output interface. This helps prevent strong signals at the output from coupling back to the input and causing self-oscillation. This isn't very obvious in this particular circuit because it doesn't have many inputs and outputs. For example, take the power supply. The power should go into the MCU first, and then the MCU controls other parts. You shouldn't let the power supply loop around to other components first, then come back to the MCU, and then have the MCU control other parts, creating a crossover with the power supply. Isolate noise sources from sensitive sources. Physically separate noise sources such as relays and switching power supplies from sensitive sources like analog signals and preamplifier inputs, keeping them far apart. The most important rule is to strictly prohibit high-speed digital signals, especially clock lines, from passing underneath sensitive analog power supplies. When analog and digital circuits coexist, you need to separate the analog and digital circuits and, if possible, route the analog ground separately instead of sharing a common ground. By mastering these 4 major layout principles, your PCB design will have a clear direction and a professional approach. A PCB with clear logic and a well-organized layout not only looks pleasing to the eye, but also fundamentally ensures circuit performance and reliability. Remember, excellent layout is half the battle. Alright, that's all for today. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.